Okay, so we are dealing with separation of variables, and we have come to an equation where we have phi double prime equals minus lambda phi, and we know that phi of 0 is equal to phi of 1, and they're both equal to 0. And I mentioned in a couple of videos ago that this is a different setup than you've probably seen before. Typically, when you see a second order equation, you have like two conditions at 0. Phi of 0 equals something, phi prime of 0 is equal to something. That's an initial value problem. Whereas here, we know phi at two places, 0 and 1. And we saw in this case, I asserted, but I haven't proven it yet, but we saw in this case that only certain values of lambda are going to give a solution, a non-trivial solution. That is a solution that's not identically equal to 0. Okay, so for example, if lambda is positive, if we assume a priori, which I'm going to prove in this video, but if we assume a priori that lambda is positive, then we know that lambda has to be, or we know the square root of lambda has to be of the form k pi, or if you square that, you get that lambda has to be k squared pi squared for all of the integers k equals 1, 2, 3, 4, so on and so forth. Okay, so in a case like this, when you have a differential equation that's sort of in this form right here, and you have this parameter lambda, the function phi is called an eigenfunction. And the scalar lambda, is called an eigenvalue. So phi is an eigenfunction, and lambda is an eigenvalue. Okay, and it's simply because if we think about the differentiation operator as the double derivative here as being an operator, let's call it L, we can write this as L phi equals minus lambda phi. And so what we have here is that in this formulation, at least, well, it's sort of like a matrix vector thing. This is what, if you think about phi as being a vector, this gives us a matrix vector similar equation, right? This is exactly what the eigenvector eigenvalue equation is for a matrix. MV is equal to lambda v. Now the only hitch here is that lambda is the eigenvalue, not minus lambda. So typically, when we think about it in this scenario, we want to write it in this equivalent form, and now L is equal to minus the second derivative. So L phi is equal to minus phi double prime. Okay, and again, the reason that we want to have a minus here is that we know lambda is positive, and we have this equation here, and if lambda is positive, if lambda is positive, then we write the solutions as, cosine square root of lambda, that sort of thing. Okay, sort of a more fundamental reason is that the minus second derivative is a positive operator, okay, which means a lot of things, but it's one of the things that I'm about to show you here, that the eigenvalues are going to be positive. So that's what I want to show you now. So what I want to show you now is that if you have an equation, if you have this function in a lambda that satisfies this equation and these boundary conditions, then that's enough information to prove that lambda is positive. Okay, that's enough information to prove that lambda is positive, and that's what I'm going to show you now. And the computation that I'm about to do, you might be like, why are you getting this? Why would you think what to do? Or why would you think that this is the thing that you should do? Well, again, very similar to what we saw in the last video, this is a very standard computation that we're going to see that really is motivated by very similar things that you would do in a linear algebra class. For example, to show if a positive, to prove whether or not a matrix is positive definite, that sort of thing. If you hadn't heard that term yet, don't worry about it. Just, here's what we're going to do here. I'm going to integrate phi squared from 0 to 1. Sorry, forgot this again. Now, phi squared, of course, I can write this as the integral from 0 to 1 of phi of x dx. Now, we're only dealing with real things. If you're dealing with complex things, this would be the modulus of phi squared. and we would have something like that as well. So phi bar. Okay. All right. So now using this equation over here, I know that phi is equal to minus 1 over lambda times phi double prime. So this is equal to minus 1 over lambda times integral from 0 to 1 phi double prime of x phi of x dx. Okay, so what I want to do now is I want to get this back to being a positive integral. Okay, and how can I do that? Well, if I integrate something positive or something non-negative, I know this is going to work. And let me just point out, I didn't mention it before, we're going to assume for now that lambda is not equal to 0, and after we do that, I'll prove that lambda cannot equal 0. Okay, so how can I do this? How can I integrate a non-positive or a non-negative thing? Well, if I move the derivative from there to there via integration by parts. So we're going to have minus 1 over lambda, okay? And if we think in terms of the standard notation for integration by parts, this would be like our v prime. This is going to be our u. So it's going to be u times v. So we've got v is going to be phi prime of x. Let me write it like this. Just phi prime times u, which is phi, and we're evaluating this from 0 to 1. And then it's going to be minus the integral from 0 to 1 of phi prime of x squared dx. Okay, now here's where the boundary conditions are going to come in. I know phi of 1 is equal to 0 and phi of 0 is equal to 0. So this is equal to 0. And so now what we're left with is minus 1 over lambda times minus gives us 1 over lambda times integral from 0 to 1 phi prime of x, this whole thing squared, dx. Okay, so what do I have on the right-hand side? I have this integral is non-negative, and if and this integral here is non-negative. Okay, now I know this is actually positive. So if phi is not the zero solution, which again we're assuming that it's not the zero solution. If phi is not the zero solution, this integral is positive. Like it's not merely non-negative. I know that it is a positive number. So if I come over here, 1 over lambda, there's no way that can be equal to 0. And so it means this integral has to be strictly positive. So I have positive is equal to something times positive. So therefore 1 over lambda has to be positive. Because if 1 over lambda was negative, this would be negative. So 1 over lambda is positive, therefore lambda is positive. And again, we're assuming that lambda is not equal to 0. So what this argument here shows, this actually shows something a little more general. Again, if we're assuming lambda is not equal to 0, this proves something a little more general. It proves whenever phi prime times phi, whenever this is equal to 0, then lambda is greater than or equal to 0. Okay, because if we don't have this assumption here, then we can't make that assumption. But this argument right here shows that if phi satisfies a boundary condition like this, then the eigenvalues have to be greater than or equal to 0. This argument shows it has to be greater than 0, and then we have to allow the possibility that in certain circumstances it could be equal to 0. Okay, so in other words, one boundary condition that would give us this would be phi of 0 equals phi of 1 is equal to 0, and that gives us something like this. But notice a boundary condition like this would also give us the same, that would also be 0. Or a boundary condition like that, which would also give us 0. Or a boundary condition like that would also give us 0 there. Or other boundary conditions. So as long as phi satisfies a boundary condition like this, this shows that if it satisfies this differential equation and a boundary condition like this, then the eigenvalues, this argument shows that it has to be greater than 0. It doesn't say anything about equaling 0, so we still have that possibility. Okay, now in this particular case, where we have these boundary conditions, when we have these precise boundary conditions, we can actually assert something even more. We can assert that lambda is not equal to 0. Hold on. Okay, we actually know that lambda is not equal to 0. And why is that? So let me separate this argument over here. Let me do it in blue so we know it's a different argument. Okay, so this is the case, the case where lambda is equal to 0. Okay, well if we come up here, if lambda is equal to 0, this means the second derivative is equal to 0. So if you have a function of one variable and the second derivative is equal to 0, it has the form phi of x equals ax plus b. So if you look at the boundary conditions, I know that 0 is equal to phi of 0. If you plug in x equals 0, you just get b. So that tells us b has to be equal to 0. Okay, if you plug in 1, you get 0 is equal to a times 1, which is just a. So that tells us a has to be equal to 0. So then a is equal to 0. So phi of x is equal to 0. So the only solution to this is the trivial solution phi. We don't care about that because that doesn't help us build solutions to differential equations or really do anything else. Okay, and so what this tells us, again, for the more general bound, if you have a function that satisfies this equation and the more general boundary conditions, that is this is equal to 0, it means the eigenvalues have to be non-negative. That is, they cannot be negative. If in addition, it satisfies a boundary condition like this, or maybe other boundary conditions that in addition shows that lambda cannot be equal to 0. Okay, so when you have these boundary conditions, this is called Dirichlet boundary conditions, and lambda equals 0 is not an eigenvalue, but in the example that we see after this, if you know phi prime of 0 and phi prime of 1 are both equal to 0, it still satisfies a more general boundary condition. Okay, so the eigenvalues are not negative, but lambda equals 0 is an allowed eigenvalue here. Okay, in this case where the derivatives are equal to 0. Okay, that's it for this video. In the next video, I'm going to show how we can solve the wave equation using the method of separation of variables.